Okay, let's see. Yeah, this you'll see quite often, I think, as the standard multiple regression equation. Or actually what we should do, but often forget, is add something over here, epsilon for the residual, because that's the actual model that we need, and we need some statistics in a minute. Thus far we didn't do any statistics, right? We only tried to fit a line through a cloud of dots. There's no normality, no probability, no nothing involved there, but in the end we do need this. Multiple regression is so standard, if you have statistical software, it doesn't matter what it is, it can run multiple regression. This is old, it's easy to implement, it's a closed form solution, so there's no complicated optimization going on behind the scenes. You can do this in any kind of package. We'll use data, but just to show you that we do not use that because the multiple regression is so weird, but it's simply one of the standard things that's in there all the time. You could wonder, however, yeah, linear, isn't that a bit simplistic for all these to have a separate effect on y? Couldn't there be all kinds of weird interactions going on that, yeah, if the number of kilometers per year is larger than 20,000 and you're not religious, then all of these kind of things might happen. But very often for data sets like the kind that we are typically collecting, we very regularly have ideas of the kind, well, we think that if this variable increases, then the target variable will increase as well, or will decrease, and nothing more specific than that. So this is not physics where you could have, let's say, a really complicated equation that we also know or is supposed to hold, and then we can test it. None of that is necessary most of the time. And in fact, even if you would have it, then let's say a first order Taylor expansion, if you happen to know what that is, would be linear and would give us a linear approximation of the thing that we're after. So very often this is actually good enough, and we do not need any complicated stuff. And the second argument here that we need is that yeah, it has to be linear in the variables themselves. So we can easily do something like this, where we include the number of kilometers per year squared, or the square root of that variable, or some other kind of transformation. As long as we keep this separate, then still this can be estimated. So here we are trying to estimate the best fitting parabola of kilometers per year as a predictor for dangers. That can actually work. The only thing that cannot work in multiple regression is something that looks like this, where we cannot separate all these different things, although if you look at the first order Taylor expansion of this, it would also be nicely linear. So this cannot be done with multiple linear regression, and in fact it can be done with something that's called nonlinear regression. So it's not that statistics is out the window here, it's just that you need a different kind of procedure. Okay, so one final bit on why this is so beautiful. Well, one is this thing that we already looked at. You can account for all kinds of intervening factors. So you could think, when we see an effect of, yeah, there is a difference between males and females, yeah, but this could be because of this, because of that, because of this, because of that. Well, if you have all of these measured, you can simply include them and control for it. So then all arguments of the kind, well, but in kilometers per year, very important here, that is simply explained away. We included that, we controlled for it, and we shouldn't bother about that anymore. Second thing is, as soon as you know what multiple regression is, you should be able to see that quite a few of the things that we did before and that we will do are actually special cases of multiple regression. One would be a t-test, I'll show that in a minute, so that two groups and we have an interval scale variable that we want to compare. We did that already. You could also do this with multiple regression and would give you exactly the same results. We'll look at ANOVA, or analysis of variance, when we compare between more than two groups. There are separate commands to do this. In fact, you could also do it with multiple regression. It's exactly the same. So not almost, but really exactly the same. Correlation, we had that before, and there you already saw that this is actually the same, or can be achieved also by standard simple regression, 1y, 1x. So as soon as you know how that works, you know how quite a few of the other ones work, and even the stuff that we won't treat here, but it is, let's say, slightly more complicated, is sort of multiple regression with a twist. Okay, so you want to predict, let's say, a target variable y that's not interval, but that is binary, could happen, then it's called logistic regression, and that is just multiple regression, well, slightly different. So as soon as you understand this, you're good to go also for the more complicated stuff. Let me show you how the t-test works. T-test is a special case of multiple regression. There I'm regressing dangerous on female. I got that minus 0.66 and at 1.48 again. I could have done that as well using a t-test, as long as I abstract away here from the stuff that we need to test, so normality for both groups and stuff like that. If I would type here t-test dangerous by female, then you'll see, I think I have that, yeah. First of all, that minus 0.6641665, that you exactly see that here too, the difference between the two means, and also that the significance test, there the test value that we have here is 6.68, is exactly the 6.68 that we have over there, and given that these numbers are the same, we also have that the significance values are the same. It's here not so easy to see because they are so small, but this 0.0000 is the same one as over there. Do note, by the way, that to get the equivalence, the unequal has to be left out. Because if you do unequal, then the significance values are calculated slightly differently. But in any case, they are the same, and you can calculate them in both ways. Okay, let's see. One more thing to show in terms of notation. These hats above the coefficients, this usually denotes predicted values. So the B0s is when we do not know them yet. When we have estimated them using stata, then we call them B0 hat, B1 hat, and so on. And if I actually calculate a prediction for each and every case in my data, that will give me a predicted Y hat. And these hats are typically for prediction purposes. Again, we have a measure of deviance that's nothing different, I should say, from the simple regression case. We look at the actual Y minus the predicted Y. We square that difference, and we sum it, and that is being minimized behind the scenes. So we have again these sum of squared residuals as we had it before in standard regression. We have that here too. If you are, let's say, a visual learner, you can think about this, where we have an interval x here, then we have a line through a cloud of dots, but then on a piece of paper. If you have two of these predictor variables x, each and every one of them also interval scale, then we have this, a cloud of dots in 3D. We're trying to fit a plane through that cloud of dots that fits best. Obviously, if you have more than two x's, it starts to be complicated to visualize. We're not so good at more than 3 dimensions, but in principle, the same thing is happening there. We're trying to fit a cloud of dots as good as we can using the predictor variables that we have.